In this lecture, I will continue the load study section, which is part of the Load Characteristics chapter. If all connected loads are known in details, like in the previous examples that were presented in the previous lecture, then it is possible to determine the total connected load per class, and use the demand and diversity factors to estimate the total maximum demand, which can be used for sizing the feeder, transformer, and distribution board equipment. However, in many cases, it is not possible to know the details of each possible connected load, which makes the above method not convenient, and difficult to implement. So, is there other ways of conducting simple load study? Yes, there are other simple methods. And that's what we will see in this lecture. So, let's look at some other methods. For simple load study and calculation model, we can use for instance, the load densities, which are defined by standards and codes, for different types of loads and building occupancies. However, it is sometimes necessary to confine our calculations, taking into account the following 6 features: building placement, building structure, level of comfort, air conditioning option, technical characteristics, and building automation or technical building management. Another load study procedure is described by the following algorithm and flowchart. First, we define the type of occupancy, for instance, a school, mall, house, hospital, stadium, etc. Then, we classify loads into lighting, air conditioning, general appliances, etc. After that, we determine the building functional areas for each class, in square meters. Then, we use the load density provided by standards and codes, such as IEC and NEC, to estimate the load capacity for each class. Then, we use related demand factors, to estimate maximum demand for each class. Next, we calculate the total maximum non-coincident demand. Then, we use the diversity factors, to estimate the total maximum coincident demand. Finally, we use the calculated maximum demand, to size the main feeder, transformer, and distribution board equipment. Now, let's see examples of load classification for non-industrial loads. First, we have lighting and illumination class. It includes indoor and outdoor lighting, being normal or emergency lighting. Second, we have a class of small appliances, which consists of general purpose sockets and office appliances, TV, and refrigeration. Third class is the space conditioning such as heating, ventilation, and air conditioning. Fourth class includes water pumping, sewage, firefighting, and water heaters. Fifth class consists of light loads, such as alarms and telephones. Finally, the sixth class includes dynamic loads such as lifts, elevators, and escalators. Now, let's see the industrial load classification. The industrial loads are usually classified as heavy, light, and moderate loads. Here, we need to note that the load study for the industry requires a bit of information about the type of loads. In all cases, load estimation is based on experience and occupancy per area. This stage is very important in licensing, estimation of appropriate transformer rating, and sizing of space required for the electrical components. Let's consider some typical load densities. Utilities supply a broad range of loads, from rural areas, with load densities of 10 kVA per square meters, to urban areas, with 300 kVA per square meters. Some typical load density values are as follows. For instance, in the case of buildings. For lighting, the load density is about 10 to 25 watts per square meters. For air conditioning, the load density is between 1 and 3 kilowatts per equipment. For office buildings, the typical load density is about 100 watts per square meters, or 2 kVA per workplace. For lifts, the load density is usually between 10 and 50 kVA per lift. For hotels, the load density is between 3 and 4 kVA per room. These are just few examples. When you conduct distribution system design for a specific country, you have to follow its specific code. For industrial and trading centers. For instance, for repair workshops, automatic lathes, weaving, and spinning mills, the load density is between 50 and 100 kilowatts per square meters. For machine tool manufacture, mechanical workshops and welding plants, the load density is between 70 and 300 kilowatts per square meters. For press shops, hardening, steel melting, and rolling mills, the typical load density is in the range of 200 to 500 kilowatts per square meter. Now, let's see some examples of codes used for estimating general lighting loads, according to building occupancy. In general, we can consider that illumination represents from 20 to 50% of total electrical load. The illumination load density ranges from 3 watts per square meters, as in storage spaces, to 50 watts per square meters, as in stadiums. Of course, this range varies according to the standard used. Besides, the range for watts per square meters has changed over the years, due for instance, to the use of energy-saving lamps. For example, the American NEC 220-14 standard provides the specific lighting load density according to different types of occupancies as illustrated in this table. For instance, for banks 25 watts per square meters is a standard lighting load. Notice that some values are provided as single ones and some others are given within a range. This is because some types of occupancies have different categories of the buildings such as clubs, stadiums, hospitals, hotels, schools, and stores. This table shows another example, that is the Kuwait code for lighting. Notice that each code has different classifications of the types of occupancy. Now, let's see how we can determine the equivalent load for general-purpose sockets that we can find in different occupancy spaces. Many methods are used for estimating the loads on general-purpose sockets. For example, in some cases, it is estimated that each socket can carry up to 180 VA. Or each socket carries 1.5 amps under 120 volts. Or, using tables of values according to the load itself, as in the table that we will see in next slide. Generally, we can say that each socket must tolerate 100 watts. Unless the socket is designed for a specific load, such as 500 watts, for an electric water heater socket. In general, the number of general-purpose sockets, connected on one radial, is between 2 to 5. According to the Kuwait code, shown in this table, some approximate socket loads are given in watts per square meters according to the place where these sockets are used. The presence of range in the load density is mainly due to the electronic and computer load increase in recent years. Note that, this type of load increases with time. For example, in the past it was 20 watts per square meters, then this number increased recently to 50 watts per square meters. Now, let's consider the general purpose appliances which have fixed electric connection and wiring. These are appliances for general use, such as lifts, escalators, and water pumps. This type of load is usually selected by the mechanical engineer during the building utilities system design. The typical value for the lifts are 15 to 25 kilowatts, depending on the building height and number of users. Typical values for water pumps are 5 kilowatts. Next type of load is the general air conditioning loads classified according to type of occupancy. The IEC standards provides typical values shown in this table, while the Kuwait code uses slightly different values as shown in this table. Again, note that each code might have different classifications of types of occupancy. Now, let's practice using codes through the following example. In this example, we consider a 4 floors office building, with a floor area of 2,000 square feet. We need to calculate the total preliminary electrical load for the transformer feeding this building, by using the following tables from IEEE standards. The preliminary electrical load is based on a transformer load level of 70%. Here is the IEEE standard for the prospective unit lighting power allowance in watts per square feet for gross lighted area of the total building. We will need this table to estimate the total lighting load in the building. This table shows the IEEE standard for typical appliance and general purpose receptacle loads, excluding plug-in type air conditioning and heating equipment, which is managed by separate standard values, which will be seen in next slide. For instance, the typical office buildings high and average values are load density is 0.5 volt amperes per square feet, and the high value is 1.5 volt amperes per square feet, so the average is 1 volt amperes per square feet. Finally, this table shows the typical connected electrical load for air conditioning only. We will need this table to estimate the air conditioning load. Now, let's start solving this problem and answering all the questions. We start by estimating the lighting load power density as follows. We know that the total area of the 4 floors office building is 4 times 2,000 square feet per floor, which is equal to 8,000 square feet. So, referring to the standard table, we can notice that we need to consider the second column, which is for areas ranging from 2,001 to 10,000 square feet. Since the building is for offices, then we can read from the table that the lighting load density in this case is 1.81 watt per square feet. Next, we shall estimate the office building average general purpose receptacle load density in volt amperes per square feet. For that, we need to refer to the related IEEE standard table. From this table, we look at the office building's type of occupancy and read the corresponding average unit load density. In this case, it is 1 volt amperes per square feet. Now, we need to determine the air conditioning load density. For that, we shall consider the related IEEE standard table that was given earlier. Again, we shall select the row that concerns office type of building, and read its corresponding conditioned area load density. In this case, we have 6 volt amperes per square feet for the office building air conditioning load density. Now, let us summarize what we have done. The total gross area of the building is equal to 4 times 2,000 square feet per floor equals 8,000 square feet. The building type and usage is for offices. The different types of load densities, that were determined from the IEEE standard tables, are as follows. 1.81 watts per square feet for the lighting. 1 volt amperes per square feet for the small appliances. And 6 volt amperes per square feet for the air conditioning. Consequently, the subtotal's estimated electrical loads will be as follows. For the lighting, it is equal to 1.81 watts per square feet times 8,000 square feet, equals 14,480 watts. Considering an approximate unity power factor for the lighting, we can also express the same value in volt amps. For the small appliances, it is equal to 1 volt amps per square feet times 8,000 square feet, equals 8,000 volt amps, or watts for a unity power factor. And for the air conditioning, it is equal to 6 volt amps per square feet times 8,000 square feet, equals 48,000 volt amps, or watts for a unity power factor. Notice that, we have converted all units into watts, by considering a unity power factor, which simplifies the estimation of the total load. The preliminary power factor of 0.85, given in the problem, will be used later. Indeed, the total estimated electrical load for the building can be calculated as the sum of the 3 types of load power. In this case, we have 14,480 plus 8,000 plus 48,000 equals 70,480 volt amps, or by rounding up, we can consider that the total estimated load is 70.5 kVA. Based on the problem statement, we know that the transformer maximum load level should not exceed 70% of its rating. Therefore, the transformer power rating, for the building, equals 70.5 kVA divided by 0.7, that equals 100.7 kVA. Note that, in some regulations, this load can be fed directly from utility low voltage network, without the need for a transformer substation, inside the user's premises. The preliminary power factor of 0.85, given in the problem, will be used later. In this case, we have a high-rise office building, with a shopping arcade. The power supply has to be planned for a 10-story, 12 floors, building, with a floor area of approximately 1,350 square meters. The power supply has to be planned for a 10-story, 12 floors, building, with a floor area of approximately 1,350 square meters. There are 2 utility rooms for technical equipment, that are located on roof level, and have an approximate area of 105 square meters each. We want to calculate the main electrical service size for this building, which is the transformer rating based on the same consideration of 0.85 power factor and 70% maximum loading. We are given this standard table, for the estimation of the average power demand, based on the building use. To solve this problem, let's first consider the case of availability of grouped load density information for each type of space. Hence, we can proceed with the calculations as follows. First, we know that the building can be divided into the following spaces: parking garage and utilities areas, including roof area. shopping center and bank. And the remainings are offices. After defining and grouping the different types of spaces, we start by calculating their gross areas as follows. For the parking garage and utilities areas, including roof area, we have the basement levels -1 to -3 with 1,350 square meters each, plus 2 utilities area of 105 square meters each. So, we have 3 times 1,350 square meters, because we have 3 basement levels, plus 2 times 105 square meters, because we have 2 utilities area on the roof, which lead to a gross area of 4,260 square meters for the parking garage and utilities areas. For the shopping center and bank, which are located on the ground level 0, with a total area of 1,350 square meters per floor, leads to a gross area of 1,350 square meters. Finally, for the offices, since they are located on floors +1 to +10, which means 10 floors, with an area of 1,350 square meters per floor, we get a gross area of 13,500 square meters for the offices. After finding the gross areas of the different groups of spaces, we need to find the corresponding load density based on standards. For the parking garage and utilities areas, including roof area, we assume that the average power demand of 10 watts per square meters. Note that, we considered the maximum value of the given range, for security margin. For the shopping center and bank, we can assume an average power demand of 60 watts per square meters. Note that, the value of 60 is selected, because it is the maximum demand for shopping center, which is also within the range of the bank average demand. Finally, for the offices, we assume an average power demand of 50 watts per square meters. Now, to estimate the electrical load for each space, we multiply each space gross interior area by its grouped load as follows. For the parking garage and utilities areas, including roof area, the estimated electrical load equals 3 times 1,350 square meters plus 210 square meters, times 10 watts per square meters, which equals 42,600 watts. For the shopping center and bank, the estimated electrical load equals 1 times 1,350 square meters times 120 watts per square meters, which equals 162,000 watts. Finally, for the offices, the estimated electrical load equals 10 times 1,350 square meters times 110 watts per square meters, which equals 1,485,000 watts. Now, we sum all the estimated electrical loads, for all spaces, to get the total preliminary electrical load, for the whole building. So, the total preliminary electrical load for the whole building equals 42,600 watts plus 162,000 watts plus 1,485,000 watts, equals 1,690 kilowatts. Therefore, the established total power demand determines the required transformer output. The determination is based on a 0.85 power factor and a transformer maximum load level of 70%. Thus, the transformer output rating equals 1,690 kilowatts divided by 0.7 times 0.85, which equals 2,840 kVA. Let's see another way of solving the same previous example problem, if individual load densities are known, for each load type, as shown in this table. Note that, all load densities are given in watts per square meter and not volt-amps per square feet like in the previous example. Based on these given load densities, we shall calculate the main electrical service size, for this building. We can use a table, to summarize all the calculation steps, as shown below. We first start by calculating the areas for each space, and insert them, in the second column. Then, based on the given table, of load densities for each type of load, we fill, the third and fourth columns. In the fifth column, we calculate the estimated load, by multiplying the load density, and the corresponding area. Finally, we sum the estimated loads to calculate the estimated electrical load, in watts, for each space group, and insert them in the sixth column. Afterwards, we sum all these estimated electrical load for all spaces, and calculate the total estimated electrical load in watts. We now apply the 0.85 power factor, to convert the electrical load, from watts to volt-amperes. Note that, here since all power densities were given in watts per square meters, and not in volt-amps per square meters, we need to apply the given power factor to convert watts into volt-amps, because transformers are usually sized based on their apparent power, and not active power. Then, we apply the 70% maximum transformer loading ratio. Therefore, we find the minimum required transformer rating. Of course, the actual transformer rating may not be equal to exactly 1270 kVA, but should be selected among the closest higher standard rated values. I hope that these examples have given you some practice on how load studies can be performed. Note that, there are no exact values, but rather rough estimates, which depend on the local standard adopted by the utilities, and the available information provided for the building space and loads. This is the end of this lecture. I hope that it was clear and informative. Thank you for watching.